again, I am a bit of a mix of things. I kind of a physicist, kind of a philosopher, technically now in a computer science group. Don't ask me how. But I'm here basically trying to do a little bit of kind of on the ground, what I, in a kind of rough and ready sense, would call phenomenology. Again, not in the formal proper sense, obviously. I'm sure there are plenty of things that don't necessarily meet in this. But I'm going to present to you an interesting phenomenon, or a set of interesting phenomena. And I'm going to want us to talk about it. Actually, towards the end of my talk, I've left a bit of time for us at the end just to have a bit of a kind of group discussion. Because I thought, it's a room full of philosophers and philosophically minded physicists. I thought it could be really useful for helping to interpret something that has just been puzzling me for a while. So the work I'm going to initially be presenting, the more technical physicsy bit, we published in Quantum Science and Technology earlier this year, alongside Tomonori, San, and Holger. But don't worry, this isn't going to be entirely technical. Hopefully I won't lose too many people. But so long as you vaguely know what discrete Hilbert spaces are, we should hopefully be okay. So, interaction-free measurement. Quantum mechanics is notoriously counterintuitive. I feel like that's a statement I can get away with for free here. And very few effects in quantum mechanics are as counterintuitive as interaction-free measurement, where effectively we're using interference to see what would have happened. I say already starting to make slightly strained noises because I'm sure there are going to be some issues with the interpretation of this. If we had probed an object without probing the object. And the kind of the type case of this came about 1993, interaction-free measurement, or the Elitzer-Weidmann bomb tester, originally published by Avshalom Elitzer, and someone who I'm sure most people here in this room will know or have had an argument with, Lev Weidmann. The actual experiment itself is relatively simple. I mean, started out as a thought experiment, but has been done experimentally a number of times. We have a single photon, which is coming from our source here. It hits a 50-50 beam splitter, splits. Ignore the bomb for the moment. The two elements of the wave function recombine at the second 50-50 beam splitter, and if your experimentalist has done everything right, if the phase all matches nicely, it should always go to this detector here that we call D1. What happens, though, if we have a bomb here? This bomb, we want to know whether it would blow up without blowing it up. Because if the bomb's blown up, then knowing whether or not it would blow up is kind of useless for us. So we're trying to see if it would blow up without blowing it up. Classically, not something we could do. But quantum mechanics, kind of weird. Let's see if we can use it here. So this bomb, effectively also we're viewing as a non-demolition single photon detector, just for the sake of making things a little bit easier or difficult, depending on if you are looking in the formalism or looking and actually having to experimentally cobble this thing together. Now, if the bomb doesn't work, regardless of which path the photon goes on, which actually isn't something we really need to consider because we're not inserting a measurement in that case, the photon will always arrive at D1. We will always get clicks at D1. If the bomb would work, and when doing this kind of effective which path measurement that would cause, the photon went on the bomb's path, obviously, bomb blows up. We don't get a click in any detector, and we lose our apparatus. The fun, weird thing happens in the case where the bomb would work, or the bomb does work, but the photon in that measurement is seen to be on the top path, the path that the bomb isn't traveling on. In this case, because we lose this kind of interference happening at the second beam splitter here, we get a 50% chance of getting a click in D2, which means, working backwards, if we get a click in D2, we know two things. One is that the photon didn't go on the path with the bomb, and two is that the bomb would have blown up, but didn't. We get a counterfactual inference. Now, just to sort of see, partly because, I feel like getting people here linked to the lab more is probably going to be a really useful thing, getting to kind of see the phenomena of what's going on here. This is something an experimentalist friend of mine put me onto. It's a little, basically, online lab bench. And yeah, we can use it to do the Elitzer-Weidmann bomb tester experiment, assuming, there we go, there's my mouse. So at the moment, we're just looking at detections. We can kind of look into a picture of visualizing where the interference would go later on, but I wanted to first just show you in terms of clicks, because this is what in the lab we would see. Now, in this case here, let's turn it up a bit. where we're kind of, the bomb doesn't work. Effectively, what we see is, as mentioned, clicks only in this detector here, our analogy of D1. We just get continuous number of clicks. This would keep going ad infinitum. If we switch it, we make it so the bomb would work. We start getting, obviously, some clicks in the case where the photon goes on the bomb path. But we also get clicks up here. Now, obviously, again, this is probabilities and probability distributions, which is why we're not getting a perfect, 50%, 25%, 25% distribution. But if we did it enough, if I dial this up to 100 and speed this up a little bit, then eventually it should, of course, tend to this, because that's what probability distributions are. They're kind of, if we take that frequentist limit to infinite, that is at least one way of kind of capturing this idea of probability. Now, the more interesting thing, as I said, is what happens to the components. Now, I kind of wish, really, rather than little wave packets, which is what we're going to get, it almost showed you the kets traveling through, because that would, again, show that this is an imaginative illustration. This is not physically what happens. We don't really see little wave packets traveling through here. But it just gives us a nice way of thinking about this kind of interference we're seeing, that we always get this interference coming through. Again, let's speed it up a little bit, such that we always get this interference going on here. And always see this. And again, if we turn it so that the bomb is on, and play, there we go. We start getting our range of clicks through. And again, it's interesting. It's weird. It's one of the first things I saw when I was looking, at paradoxes in quantum mechanics. And it made me think, partly, what can we do with this? Which actually a lot of people have kind of taken this Elliott-Seidman bomb tester and actually tried to apply it. In fact, something I find both interesting and slightly terrifying is there was a paper in Nature in 2006, the Pourquiet paper, where they effectively had a setup like this, but rather than a bomb, they had an optical quantum computer doing Grover's algorithm. And for a while, this was the most effective way of doing Grover's algorithm, was counterfactually computing Grover's algorithm. I think it was for a good few years. Partly that's obviously 2006. Quantum computers weren't great, but also, again, it just shows you the power of this kind of peculiar counterfactual interference-based effect. And again, actually, if we go to, oh, no, that is not the button I wanted to press. There we go. Actually, a webcomic artist, Zach Wienersmith, who publishes SMBC, has made a webcomic on this. Which, again, in case you didn't think that I was a nerd before, this is from my thesis, whereas one of the quotes in front of a part, I quoted this webcomic. I know various people love to deploy the fun Feynman quotes that, to some degree, the only mystery in quantum mechanics is interference. I think to some degree that's debatable, but equally, things like this, where we're getting these peculiar effects from interference, to me are at least something we should look at and think about, which I don't think is necessarily caught in what a lot of philosophers of quantum look at, which is, again, the typical hydrogen atom or cloud chamber tracks or things like that. I think looking at these kind of interferometers, if we want to be specific, is something that is really useful. So that's what I'm going to be doing today. I'm going to be talking to you about interferometers. So this is a nice generalized interferometer, a generalized case of that thing that we saw. The thing we saw had two paths. This can have an arbitrary number of paths, a finite but arbitrary number of paths, an arbitrary number of inputs, an arbitrary number of outputs here with detectors. And we are going to play a game. We are going to guess whether this little absorber here was present or absent on path A. Now, we kind of treat our prior of this as effectively being, complete uncertainty for the sake of starting off with our nice prior. So 50-50. Again, you could debate that. I'm going to, claim to justify it in a Bayesian way, but I'm not going to actually try and do that because, I'm not a philosopher of probability. I just tinker with it. And so what we're looking at is based on a single trial, a single click in one of those outcome detectors. We are trying to see whether or not we can infer that this absorber was present or absent, or rather what the chances of us guessing, of our guess based on this being wrong. Now, our strategy is going to be this. We're going to compare the probability for that detector where we get our click with and without the absorber. If the absorber reduces the probability, so if the probability PM, which we're going to say is the probability PM without the absorber being there, is greater than the probability, we call it PM given absorber, then if we detect the photon at M, our best guess is going to be that the absorber wasn't there. And classically, that's all we need to think about. Because really, unless we start trying to renormalize or things like that, so long as in our big probability, we're considering also the probability we lose to that absorber, the only thing putting that absorber in is going to do to the probabilities at the end is either keep them the same or decrease them. But quantum mechanics comes along and does some very different things. We need to consider this weird probability that, again, this is in an unnormalized case. This isn't where we're just looking at the outcomes. This is where we're also including the absorber as one of these outcomes. But putting the absorber in can somehow increase the probability of this photon going to these outcomes or one of these outcomes then. In this weird case, if we observe the photon in that outcome, then our best guess is that the absorber was present. And these kind of weird counterintuitive cases we're going to use as the basis for what we're going to call quantum counterfactual gain. This counterfactual gain in ability to detect this absorber. Now, I'm about to go through some maths. Don't worry if you don't get it. It's mainly because, again, physics, quantum theory, we like formalizing things. The end result I'll talk through in a more sort of qualitative sense once we've got it. Basically, we want to kind of characterize our chance of being wrong in this kind of game. So this average probability of picking this wrong option, we're going to call our P error here, is basically, we're summing over the lower of those two probabilities for all the options, dividing by half. And we can, to kind of evaluate the difference between the classical case and the quantum case, we can rewrite this P error, this average over the lower probabilities. As this, where we get this statistical distance between our kind of, our classical case, statistical distance between the case where the absorber is present and the absorber is absent. Again, kind of the power of the effect on our overall probability of putting this absorber in. And classically, the statistical distance is always going to be PA. Classically, this kind of sum over the entire effect of putting the absorber in on these probabilities is just equal to the probability we lose to the absorber. In quantum mechanics, that's not the case. So we define our counterfactual gain as the statistical distance minus PA. Nice and convenient. Our counterfactual gain is just the difference in those distributions of probability, or the net difference in those distributions of probability with the absorber present or absent, minus the thing we get in this classical case, for which we are basically just summing over these weird cases where the probability of the photon arriving in one of these outcomes increases when the absorber is present, where PM given XA, which is probability of arriving in the measurement port given the absorber being there, is greater than this sort of PM when we don't put the absorber in. And we can rewrite this into these two terms here. Now, the first term looks a little bit like kind of some sort of joint probability or sort of sequential probability. Effectively we have here, in bracket notation, that's going to be the probability if we started in state A for the thing to arrive in M. And this is going to be our probability of it being in A in the first place. But also you'll see there's this little thing here, which again, we define mathematically in this way. It's the real part of the Kirkwood-Dirac function. It's a quasi-probability function, which again, in that's not fun. Okay, oh, nope. Yep. The bomb. There we go. Let's try to avoid touching that as much as possible from now on. Okay, so in the Elitzer-Weidman scenarios, or in Elitzer-Weidman type scenarios, which we called there, which again are the ones like the Elitzer-Weidman case, where effectively in the case where the bomb doesn't work or where the absorber isn't present, it always arrives in one detector. So if you get a click in the other detector, you know for certain the bomb worked or the absorber was present. This Kirkwood-Dirac term here is zero. This kind of, as I say, almost looks a bit like, again, a joint probability, effectively. We have our initial state here. We have, a projector on it going via A, and then we have this little bit here, because again, this is basically just a trace of if you stack those projectors. And again, so yeah, in the Elliott-Weimann type scenarios, which previously were thought to be kind of the most powerful for these counterfactual scenarios, this counterfactual gain as we calculate it is just going to be that first term, that sort of sequential probability. But there's a reason I called it a quasi-probability. And that is that in quantum mechanics, you would expect anything that looks like a joint probability, anything that's like, I start off in a certain state, I do a measurement and get a certain result, I do a different measurement and get a different result, that's always going to be positive. Not so in quantum mechanics. In fact, this is one of the things that has caused people a lot of trouble in quantum mechanics, is you can't define a joint probability in that way that covers all quantum scenarios. In fact, that's why I called this the Kirkwood-Dirac quasi-probability distribution. That's because Kirkwood initially tried sort of looking for one of these sort of joint probabilities, and again showed that as a property, you can add it, or in the same way you would expect for probabilities. It's sigma additive if you want to be Kolmogorov, and always sums to 1, but you get negativity, or even worse in some cases, imaginarity. Dirac then went and basically said, yeah, that's easy, so what, and did kind of the same thing in a paper, but much simpler. Don't get me wrong, I respect Dirac's simplicity on this, but I feel like he might have missed the point a little bit. And that is because in these weird cases, for instance, in this case here, where this Kirkwood-Dirac term, this sort of weird joint seeming probability for start in state, go via blocked or blockable arm, and end at detector is negative, then this counterfactual gain is higher than in the Elliott-Weimann scenario. We have more power to discriminate whether or not the blocker was present or absent. And this hasn't been explored before. Again, this work we published earlier this year is the first one we've seen, certainly in this kind of very applied case that is looking at this, that is using these specific weird cases where we get this negativity to sort of seemingly kind of power our ability to identify. Again, I realize this obviously is quite an abstract diagram. I mean, the way I like thinking about it when I'm trying to convince quantum tech people is, imagine you're trying to do imaging, and again, you have some pixel, which, could either be transparent, again, at the wavelength you're looking at, maybe, if it's white, it's transparent, if it's black, it's opaque or absorbed, and you want to work out, if it's transparent or opaque to your photon, ideally without sending the photon through it. Again, imagine you've got a very delicate archaeological sample. You've taken one of the Dead Sea Scrolls or something from Pompeii. It's this idea of being able to use this to potentially, image in these cases with a far lower chance of the photon going into the material and being absorbed by the material, but still seeing what would have happened had you sent the photon through that material. Again, the term counterfactual is one that philosophically, I'm sure when we get to the discussion stage, people are going to have issues with. But at the very least, in that kind of, quite practical definition of counterfactual, or that sort of inference of, what would have happened if you had a classical device, I feel like it is justified. Now, as I said, that interferometer I gave you was very general. Let's look at a specific one. This is one that, because Holger doesn't like naming things after himself, I've decided to force him to name Hoffman's three-path interferometer. Effectively, again, he tends to use it for exploring things like contextuality and the like. It passes through the 5 different measurement contexts you get in a Q-trit and returns you to that same context. Again, if you have sort of a 1, 2, 3 basis, it will return you to that 1, 2, 3 basis. It'll have shifted the position of the 1 and 2. So really you need to do, Feynman's hat trick, effectively go through, 4 pi in order to get back. But it's still returning you to that same context. And in the meantime, you go through various intermediate contexts. But again, I'm going to use this a bit more practically. I'm going to put in a specific state, and I'm going to use something from contextuality theory, actually. So again, we call this the NF state, and that is because in a contextual model, the claim is made that if you start with that NF state, you should never see anything in F. But we know that not to be the case. If we do a measurement in F, even when we put in the NF state, we still see something. And again, that you can use as a proof of contextuality applied into a physical scenario. Holger has published a paper on this. But again, I'm going to use this a lot more physically. I'm going to take that interferometer with this initial state, which, again, without the absorber present, gives us this, gives us, as expected, the same output distribution as we had in our input distribution. These little numbers here are probabilities. If we dunked a detector in at that point, the probability we would get a click for a given putting a photon into the interferometer. Now, what happens if we put our blocker in? Even though only 1/9 of the probability goes via the blocker, we see this massive great change, this massive focusing effect of, kind of, what's that? I'm going to say, roughly half, maybe a little bit more of the probability focusing on that middle path, even though we only have a 1/9 chance of the thing going through. So we're getting a massive physical effect, far, far larger than that PA. Again, that PA is what you'd expect classically to be, you'd expect a 1/9 change in the distribution. But that's not what we're seeing here. We're seeing this weird additional interference. We're seeing this effect of the blocking on photons that weren't blocked. How? Again, let's just show some calculation again, just to prove, that this path we're seeing this focusing on, this middle path, this path 3, if you remember, is also one where we get this negative Kirkwood-Dirac term here appearing. This minus 1/9 Kirkwood-Dirac term. Again, the first term, that sort of sequential probability, is the same for all, but again, it's this negative here. So again, I quite tentatively make the claim that this negative Kirkwood-Dirac term, or the fact that there is this negative Kirkwood-Dirac term, the fact that the scenario is designed such that it gives us this negative Kirkwood-Dirac term, is responsible for this weird focusing effect, for this increased kind of weird interference causing this massive, very visible change. Now, why? That's the thing that we're here to discuss. So again, classically, we would expect our probability distribution with the absorber to be the probability distribution without the absorber minus the probability lost to the absorber. Nice simple thing to sort of show here. Again, if you're not mathematically minded, it's basically just exactly what I said, but put into maths. Probability at a certain detector, given XA, which is detection, is the probability at that detector normally minus that sort of probability of going to path A times by probability of going from A to that measurement device. But in the quantum case, there is a difference. And in theoretical physics, when there is a difference, what we tend to do is just put a little character there. So this is our chi b. Our chi b is just representing that difference. At this stage, I'm not saying, we don't necessarily know what that is. It's just chi b. Now, again, we can rearrange this slightly in order to give us more of an idea of what this chi b is or what form it takes. This chi b, effectively, I'm going to argue more heuristically, must come from the measurement back action. This effect that doing the measurement has, the measurement of if it was in that absorber path or not, on the particles that don't go via that path. Again, this is something that classically feels very weird. The only effects we should have are those local effects from the absorber being in that path on particles that also go via that path. But that's not what we're seeing here. We are seeing an effect by putting that absorber in, by having that which path question, we then see an effect on the other particles. And to some degree, that's because we kind of lose the coherence that we would expect between that path that we now know the particle isn't on and all of the other paths. Now, again, this back action takes the form here of 2 times that kind of classical-ish sequential probability minus this Kirkwood-Dirac term. So, again, this back action term itself is only 0 when the Elitzer-Weidmann term, which is what we call this sort of first term, is equal to the Kirkwood-Dirac term, because obviously there's a minus between them. Now, this only ever occurs in 2 cases. The first is our nice trivial case, where nothing from the path of the absorber ever goes to that detector. Because again, you would expect if there's no way for anything to travel from the absorber path to the detector, it shouldn't have an effect. It's the trivial case. The other is when our initial state is effectively an eigenstate of or rather, when the absorber state is an eigenstate of the initial state, when the way that we have prepared this initial state is such that, again, it could either be that this initial state is a maximally mixed state, where again we have a mixture of it being on that path and not on that path, or it could have been prepared entirely going into that path, or it could have been prepared again in that trivial case, or the reciprocal of that trivial case, where it never goes from the start to that absorber path. Again, this is effectively mathematically informing what I just said, which is that in these cases where this back action is 0, there is no quantum coherence in the kind of input between A and the states orthogonal to A. We require that coherence between A and the states that are orthogonal to it to see this back action effect, which again kind of then informs why it's not an effect we would expect to see classically, because classically we don't really have this idea of, at least for single particles, we don't really have this idea of coherence. Again, if you're dealing with laser light or coherent states or things like that, obviously in a coherent state there is coherence, but in that case you're not doing this sort of single photon detection bit. But yeah, if you're dealing with single particles, again, in a pachinko machine where you drop a ball and there are lots of pegs and things, which is my fun analogy for an interferometer, you don't get coherences between the different paths that you could go through the pachinko machine. I feel like the game would be a lot more fun if you could. So, quantum coherence being removed by measuring on A is therefore, again, I'm going to make this very big claim, causing this back action. Or at the very least, there is correlation. The same thing might be causing both of them. Depends how you want to interpret these things. But there is a very visible link. Where one is, t'other is. So, again, cases where the back action is 0 have no counterfactual gain, as the counterfactual gain only includes terms where that first bit is bigger than 2 times that second bit, which again is obviously not the case if the two things are equal. Yeah, trivially they're not sacrificed. I preempted myself. So yeah, all interaction-free scenarios have this counterfactual gain. So therefore, this measurement back action, this chi-b term being non-zero, again, going to make a big claim here, not just these cases with the negative Kirk-Quadrat, but all of these interaction-free cases, the Elitzer-Weidman bomb tester, the counterfactual computation case, counterfactual communication, which is a fun sort of sequential back and forth thing. I'm going to say all of these effects are being caused by this measurement back action. Now, again, if we take this at face value, if we say measurement back action is therefore the cause of interaction-free or counterfactual quantum effects, and if these effects occur due to the removal of coherence, due to this measurement, us doing this measurement is removing this coherence across these things, is it really interaction-free? Is the name maybe a little bit of a misnomer? Because it feels like there is some interaction going on. It's maybe not a classically describable interaction, but it feels like us doing this Wiltsche path measurement on the system is in some way an interaction with the system, which is causing this effect. And again, because a Hilbert space is a Hilbert space, an n-dimensional Hilbert space is an n-dimensional Hilbert space, regardless if you're talking about a big interferometer or, I don't know, let's say 2 qubits which are entangled, to pick an example out of completely thin air, the Bell scenario. We can map basically all of these weird paradoxical scenarios to an interferometer, really. Again, our ideas of what counts as local regions and things are partitions, as was kind of discussed earlier in Philip's talk. We might need to reconsider a little bit, but from a quantum informational perspective, we can consider these cases to be equivalents. In fact, actually, we've got a paper basically showing you can model this. You can use the 3-path interferometer that I just showed to model the Bell case, the standard CHSH case. So in that case, is neglecting measurement back action or its wider analogy in these cases maybe the cause of all of these kind of contextuality or non-locality paradoxes? Is it because when we come up with our inequalities, when we come up with our equations that we're using to try and figure out based on our kind of classical assumptions, which we then see quantum mechanics violates, we aren't factoring in these little bits that we should be adding, kind of counting this measurement back action? Is that maybe, at least mathematically, the reason why we see quantum mechanics violating these inequalities? And again, in that case, what would such a correction term mean? I mean, for a start, in my mind, it would give us at least, a little bit more of a physical meaning to like the Searlson equality, Searlson limit. Because again, it's kind of giving us a reason from a physical effect, from the dynamics of measurement for, as I say, in the CHSH case, the correlator being 2 root 2. Which again, I at some point I need to run the maths, or rather I need to get a PhD student to run the maths, because I do not have time with grant proposals and things right now. But again, I would love to see, and again, I feel like doing these calculations in that scenario should return us effectively, if we ran it through for the CHSH scenario, should give us the Searlson bound, just from this kind of slightly I don't want to say slightly mechanistic case, but from factoring in these additional contributions to probability, which our classical worldview doesn't really allow us to think, from factoring in the effects of these coherences or their equivalent in these scenarios, which we tend to neglect when we're combining results from different measurements together. Now, this is the part where this gets interactive. We have a room here full of philosophers and philosophically minded physicists. I have just given us something with my quite rough hand-wavy interpretation. I want to see if we can make use of this resource, I say, pointing to all of you. Yes, yes, you are all resources here, even you, Guido. To try and see what we can do to make my analysis of this better. Because again, as I said, it's quite rough, it's quite hand-wavy, it's quite initial. The result we only published earlier this year. It's not something people have been thinking about since, old quantum theory. It's not, a hydrogen atom or anything like that. This is fresh off the press, quantum information, quantum foundations. Let's try and do something. So, I'm not sure what would be the best way to do it, Harald, whether you wanted to lead this part of the discussion or whether I would just point and whatever.
Who's first?
Yes, it was a speedy talk, so I couldn't follow all of it. But it seemed, I read about the earlier Weidmann.
Yes.
Earlier. But my question is simply, isn't this just a case of non-local phenomenon? And you see, if so, you couldn't really say that it is the causes of non-locality because it is just an instance of it.
Ooh. Now, see, that's firstly, what do you mean when you say non-locality? Do you mean what I would call Bell non-locality, which is ability to violate a Bell inequality? Or do you mean a kind of physical non-locality, again, what Shimony used to call passion at a distance, kind of, again, I'm probably misusing that correct, please correct me if I'm...
I guess I thought about Bell non-locality.
Okay, well, yeah. Again, as I say, it's, insofar as it's an ability to violate a Bell inequality, yes, but we don't know what causes that. We know certain assumptions, one of which should be wrong, because obviously we put all those assumptions together, we get an inequality we can violate, but that doesn't necessarily tell us much about what's causing it, or the mechanism, or what it is within measurement, let's say, that's doing this.
I would like to tag on to what you were asking about non-locality. So you're pointing to two effects here.
Mm-hmm.
The Elitzer-Weidmann bomb tester,
Mm-hmm.
and then Kirkwood-Dirac negativity.
Yes.
Could you relate these things to, and I know you can, the issue of non-locality and contextuality and back action?
Yes.
Because I think the relation is separate. It's a different relation for the Elitzer-Weidmann bomb tester than it is for the Kirkwood-Dirac non-locality. Negativity.
Yes. So, I mean, to some degree, what Jan Oker is alluding to here is we're in the process of writing a paper, basically in a far simpler way as has been done by Rob Speckens and people, showing that the very first case, this Elitzer-Weidmann bomb tester, as weird as it looks, you can reproduce the phenomenology of it classically. Again, their definition of classical is kind of based on, Jan Oker spoke a bit about this yesterday, Rob Speckens' toy model, or an extension of it with some additional bits and pieces. Their argument for that took about 60, 70 pages. In our version, we're basically just using standard non-contextual stabilizer notation, and we should be able to show it in about 2 pages. The point is, therefore, to some degree, this is something that we don't need to appeal to ideas of contextuality to represent. Whereas, again, in that same paper that we're drafting, we show that cases with negativity, cases like the more complex generalized case, or, again, the Hoffman interferometer case, because, again, I'm going to keep calling it this until Holger accepts that we're going to name it after him now. In cases like this, you cannot use that stabilizer formalism or a Speckens-style toy model to represent what's going on, unless, again, as is the case with Jan Oker's contextual ontological model, you have to add in some non-locality to it. So,
So my point was the difference here is that the Elixir Weidman bomb tester you can manage to recreate with local interactions.
Yes.
And if you got this kind of interferometer where you have a negative Kirkwood reactor, then you have to go to a non-local. That was the nature.
Yeah.
So that's a partial answer to what you're saying.
Yeah.
The first simple bomb tester. Yeah.
Let me go back to
that is low. You can handle with local hidden variables.
Yeah. This one you can do using local hidden variables. Oh, sorry, wrong. Yep. There we go. This one you can do with local hidden variables.
But in general, you cannot. That was.
Yeah. Local hidden variables with statistical independence. I'm just going to specify because otherwise Sabina would be very angry at me.
Yeah. So two comments. So one is sort of connecting this to Bohr. So yeah, thinking of sort of Bohr's reply to EPR, and we are thinking of Bob measuring position on his particle, and the way Bob conceptualizes it in the context of measuring. Let's say momentum. In the context of measuring momentum, Bob can tell, or Bohr can tell, retroactively, a story that the two particles must have exchanged a certain momentum,
Yes.
and therefore, it's possible to predict with certainty what will happen on the other particle.
Yeah.
But you are telling this sort of retroactive story, and of course, then you can use okay, the other particle has this momentum. You can use that for all kinds of other predictions, and whether you're telling a version of that, whether that's what you're doing.
So that's an interesting. I mean, first off, obviously, one reason I'm not a massive fan of thinking about the EPR argument in these cases is because, to some degree, again, that's very different to what we eventually saw with through the Bohm version, actual Bell scenarios and things like that. Obviously, having perfect correlation or perfect anti-correlation is telling us a very different thing to what we eventually realized the actual problem was. Again, it's you can come up with a local hidden variable model effectively, that would reproduce EPR correlations, but not Bell but not be able to violate a Bell inequality. Yeah, exactly, but not EPR Bohm. So I think there is separation of that in terms of the retroactive element, that's sort of the working backwards to infer. I mean, to some degree, in terms of our definition of the Kirkwood-Dirac, because we're kind of looking at specific final points, there is going to be that element of considering backwards. It's the same as actually. So the Kirkwood-Dirac term is proportional to weak values, which very much are a case of that kind of inferring, in some sense, I guess, calculationally retroactively, what this weak value was, because you do need this sort of kind of final result experimentally. You need this final post-selection, and it's only after that you can tell what the weak value. Actually, hands up, who here knows what weak values are? Okay, that's a couple. I'll mind if I quickly give a little history on weak values, just for the sake of context for everyone else. I can try. And you can correct me when inevitably I'm. Okay. So this is where I get to use other slides, assuming I can find my mouse. There's my mouse. Okay. So basically, obviously, in quantum mechanics, from reasonably early on, this idea that we could, without measurement, or without a disturbing measurement, work out what. I'm not going to say the state of a quantum particle, because obviously we can represent it as a quantum state, but work out what the values of properties of a quantum system, a quantum particle, let's say, were between measurements, is something that was kind of poo-pooed. If you have first measurement, second measurement, inferring properties that are non-commuting with those two measurements between is not something that, people said necessarily you can do. To some degree, this was until, whereabouts is going to be? There we go. That's what I want. Talks and posters. Now this is hopefully gonna, there we go. Again, it's my old university branding. Apologies for, there we are. So, calculationally, this is a weak value. Something proposed by Harald, Albert, and Weidmann in the 1980s to supposedly be able to tell us what in some sense, the value of the physical property was between measurements, regardless of if that was between measurements of non-commuting, of observables which don't commute with the thing that you want to know the property of. The only issue is their approach to doing this caused some consternation. So the original paper that introduced these weak values was called How the Spin of a Spin Half Particle Can Be 100. Which maybe is an indicator that interpreting these weak values in that sort of realistic sense as equivalent to eigenvalues and therefore equivalent to properties may be a bit problematic. So again, as I say, this calculation is the weak value. If you times this weak value by the probability, you start in your initial state, that's what this psi I is, and end in your final state, that's what this psi f is, then that gives you the Kirkwood-Dracta. So again, when we get anomalous weak values, which again are these ones where the weak value is outside the range of eigenvalues, so it feels a little bit non-realistic. Like again, if you have eigenvalues for a projector are going to be 0 or 1 for the thing being in that state or not being in that state respectively, you can get negative weak values. What does that mean? If an eigenvalue of 0 means it wasn't in that state, what does a negative weak value mean if you're interpreting it that way? I mean, that's something that we looked at last year was the quantum Cheshire cat, which actually I was thinking of bringing up to you, Greg, yesterday when you were talking about compresence of properties and things, because Harald made this fun argument that, again, based on taking weak values for certain things, you could have a particle where a property of that particle, specifically its polarization or spin, depending on how you want to look at it, was separate to that particle, traveling along a path that the particle could not be on. Yeah, last year we kind of deflated that account a bit and showed it's basically just a contextuality paradox. It comes down to the fact that, again, even with these weak values, if you try and assume that they're telling you the same thing as eigenvalues, i.e. as properties, you get problems. And so if we ignore that kind of link for the moment and instead just look at the situation, what we see in the Cheshire cat scenario is effectively 3 mutually incompatible properties. Actually, this is my first tattoo is the little contextuality diagram we did for it, whereby you can have a state that has 2 of those properties, but there is no state that has all 3 of those properties. It's like, I mean, the example I love to give credit to XKCD is you're driving along a road, you see 3 signs: no entry, no U-turn, and no stopping. I'm waiting for the faces to turn. You can't even do nothing because that would be stopping. But we could imagine a quantum system whereby if we wrangled our Hilbert space right and, made it so that those properties, were non-commuting linked to each other, we could measure and say, okay, we're not stopping. Okay, we're not making a U-turn. Okay, we're not entering. We can make it so a quantum system, if you measure it individually and then combine the results from those individual things together, looks like it has mutually incompatible properties. That is my, again, slightly rough and ready description of what contextual behavior is in quantum systems. Again, I'm sure there are probably far better versions of that, and I'm sure Jan Oker is probably going to. Yeah, so we have these contextual things. The quantum Cheshire cat is basically an example of that. It's not that we have particle going on one path, property going on another. It's that we have a contextual scenario. If you combine 2 of those properties and say against one of those properties, so associate 2 of those properties with the location of the polarization and one of those properties with the location of the particle, then having these 3 incompatible things makes it look like if you, squint your eyes and turn upside down, the particle is separated from its polarization. All that to say, I have lost track of why we were talking about weak values. Sorry, Guido. Yes. Did you get an answer that's relevant is the more important thing.
Yeah, well, I don't know. Maybe it was meant to be a sort of simple suggestion.
Okay, okay.
Here's another familiar scenario in which there's something like back action happening.
Yeah.
And, is it the same kind of back action? Can you see it? In this Borean way. In which case, yes, I mean that suggests a way of it should be applicable to the Bell scenario and so on. That was the question.
Yeah, again, as I'd say, for the EPR scenario, again, just because in the most general case, this back action, especially when we have negativity, is something that we can't reproduce using one of these local hidden variable models. But the EPR scenario is something we could reproduce in that way. I would say it's slightly different. But again, that I'd need to properly do the maths really to tell you.
Another question.
Yes.
Yes. Can you switch back to your presentation?
Hopefully.
Page 59.
Oh, okay. There we go. Is that?
That's the one.
Yeah. Oh, no, because that needs to. Yep, I'm just trying to exit it. There we go. Exit that. There we are. Where is? Get rid of that and make that bigger. And you said page 59.
I realized I had to write it down.
Huh? Yes.
Is it the next one then? Because this is not the one.
More or less.
I tried to write down a page number where it said quantum coherence is removed by the back action.
Ooh, okay.
You really mean that? Was the question.
There, yes.
56. Okay.
Yes. So remove those
because that would mean to me that what you obtain is a mixed state.
The specific aspect of quantum interference between that one path and the other paths is not present because again, I realize I'm putting almost a kind of a too much of a causal kind of aspect when it's two separate cases.
Here's where I'm going with. So I think that coherence is still there.
Yeah.
So I would have written, if I want to write it like this, I wouldn't have written re. I would have said quantum coherence is moved.
Yes.
Somehow it's rotated away.
I think I see what again, because as you say, in both cases, yeah.
As I understand it, it's still a pure state.
Yes.
If the bomb explodes, you get a mixed state. But then again, if the bomb explodes, there's nothing left of the interferometer. So
yes. Yeah, in the case where we're post-selecting, which again links slightly to what you were saying.
The bomb does not explode.
Yes. Then, as you say, it should still be a pure state here. And
expect it to be.
yeah, and so as you say, the coherence that previously was between this path and all of the other paths, in some sense, is moved to coherences mutually between all of those paths, such that the purity is conserved. Good. Yeah. I will make that a note to change that in my future presentations because that's a very good point.
All right. Thank you so much for the talk and the discussion.